3D printing is a rapid prototyping technique that's used to build solid parts directly from a CAD model by printing solid structure a layer at a time. 3D printing can be used with many different materials. We're interested in thermoplastic polymers because we can compound them with a wide variety of other materials to control final properties, making blended composites and functional materials. These thermoplastic compounds are suitable for 3D printing because they can be melted and deposited a layer at a time, really a bead at a time, to form a cross-section of your part. When 3D printing was first introduced to the aerospace industry, we were eager to find ways to apply it. We understood 3D printing could build complex structures. We realized that we could build advanced design geometries not previously possible. We knew it could build parts quickly. We could send a CAD drawing to a 3D printer, and we would arrive at a functional part within a day. So early on, we began a project to develop new thermoplastic compounds that could be used in a 3D printer and applied to our manufacturing concept. We explored a wide range of polymers and reinforcements, such as carbon fiber, nanotubes, powders, and other fillers. Each new composition designed to address engineering functionality. We extended the concept to not only control the composition and functionality of our part, but to control the composition at every location of the part, changing it on the fly as needed. We called this process pointwise composition control. Why would you want to control the material properties of a part? You might want to make a part very strong and stiff in some locations, and perhaps temperature resistant, and in other locations, you might make it transparent for communication. One of the limitations of conventional 3D printers is the build envelope. You're restricted to building in a heated oven or limited to building inside a chamber. We've mounted an extruder on a large 6-axis articulated robot so we can deposit large structures. And we've incorporated mixing and blending equipment in line so that we can adjust composition on the fly. This part was built to capture the imagination of designers. This part visually communicates that you can build a single structure with very different geometries at different locations of the part. But you can also control composition. This part happens to be graded from green to blue. This part could also be graded in thermal properties, electrical properties, or it could be graded in other types of functionality. So, let's say you're going to build a hand-launched UAV, and you wanted to build all of the electronics embedded in the wings of this small UAV. You'd want a strong and stiff structure for the internal wing, but you'd want a lightweight, durable skin and solvent-resistant material for fuel storage locations. Different functional properties require different material compositions. That's what pointwise composition control allows. If you extend this process all the way to our manufacturing concept, you could build an entire airplane. Now, if we're going to use this process in manufacturing to build a full-size cargo plane, we're going to need several robots. But that's okay, robots are cheap. The robots can be stationary floor-mounted and rail-mounted overhead on a gantry system. Several robots, all at different stations, building structure in concert, all at once. We're going to build with structural materials, we're going to build with functional materials. We're going to control density, stiffness, and material properties all over this airplane. And because we build directly from our CAD drawing, we're going to be able to quickly and affordably build complete products that have geometry and design that have not been possible before. This is the factory of the future.